Okay, let's do another example from section 6.1, number 15. Find the projection of the vector 1, 2, 1 on the subspace, the span of these two vectors. This happening in R3 because those vectors have three components. Okay, the way we dealt with this was to find a basis for the perp space to that given space. That's done. We've done an example of this type already. That's done by taking the vectors in a spanning set for W, putting them in a matrix A as rows, and finding the null space of that matrix. Okay, so let's look at a prepackaged bit of a solution for that. So we'll let W be this given subspace. So let W be the span of those two vectors there. We need a basis for the perp space, W perp. And then we'll use, as we'll look at the notes again, then we'll use these two vectors and a basis of the perp space to go through and find this particular projection that they're interested in. Okay, so W, let it be the span of these two vectors, so it is that subspace there. Note 6.1.a that we just looked at says, put these two vectors in a matrix A as rows. So here's matrix A, first row 3, 1, 2, second row 1, 0, 1. And we need to solve AX equals 0. We need to find the null space of matrix A, which is all vectors X, which are mapped to the 0 vector under the action of matrix A. Okay, so you know the story. We'll set up this homogeneous system of equations. Here's the augmented matrix. We'll do our row reduction thing, not too bad. It'll produce something of this form. I've skipped a few of the steps. There's a written solution out there for you with all the steps in it. This will translate into X being of the form a scalar multiple of -1, 1. So the perp space can be described as a span of -1, 1. So this gives us a basis for the perp space. We've got a basis for the perp space, W perp. We've got a basis for the given space, W. So what we need to do now is take a look at note 6.1.b. It describes exactly that to the notes. Okay, let's see here. 6.1.b. Here it comes. All right, to find the projection of a vector B on a space W, that's exactly what we're doing. Follow these steps. Find a basis for W. They gave us a basis for W. Find a basis for W perp. We just did that part. Then find the coordinate vector R of the given vector B relative to the ordered basis created by first the basis elements of W followed by the basis elements of W perp. Then for the projection that we're looking for, we'll take those coefficients times the vectors V1 through V sub k, where V1 through V sub k are the basis vectors for the original space W. Okay, so here's what we're up against here. We've got vector B. Let's see, so it's note, we document that by note 6.1.b. We need vector B, the vector they gave us, vector B, this guy, 1, 2, 1, as a linear combination of the ordered basis, order matters here, the ordered basis 3, 1, 2, 1, 0, 1, and this one we found down here, -1, -1, 1, 1. Okay, just to annotate a little bit, in the notation we had in the notes, these are the basis vectors for W. So this is the V1 up through V sub k. And this is the basis for the perp space. V sub k up through V sub n. Of course, there's only one over there. But in terms of the notation, we need to write vector B as a linear combination of these. The coefficients will give us the coordinate vector. So, consider. All right. We're trying to write vector B as a linear combination of these vectors. So we want to consider something of the form, let's say A times vector R equals vector B. Right, we're using R's to represent, at least we did in note 6.1.b, using R's to represent the coefficients. So let's call this the R vector. Consider this system of equations. Whenever we take a matrix times a vector like this, you'll do that row times column thing, and that will produce a linear combination of the columns of matrix A with the coefficients being the entries of matrix R. So we want those linear combinations of the columns of A to give us vector B. So consider AR equals B, where the columns of A the columns of A are the V1, V2, well, V sub 3 given here. And when we first encountered matrix multiplication, we saw this in, let me find a reference for you. Here it is, note 1.3.A. Note 1.3.A observes, hey, doing this gives linear combinations of the columns. Okay, we want linear combinations of those three vectors, and we want to get out vector B. So this is how you find coordinate vectors as well. All right, so we'll consider such a matrix A augmented with B. Okay, the matrix A will have as its columns 3, 1, 2, 1, 0, 1, negative 1, 1, and we'll augment that with the components of matrix B, 1, 2, 1. All right. So far, I don't do anything too new. We've boiled it down to solving a system of equations and then interpreting that in light of note 6.1.b. All right. System of equations. I want to do that in detail. Fine. Okay. So what you're going to do, how about we get the 1 up here in that first position. So we'll take rows 1 and 2 and swap them, because I love row reduction. Okay, 1, 0, 1, 2 for the first row. Second row, 3, 1, negative 1, 1. Third row remains the same. Why would I want to do that? I'm trying to avoid fractions, which I don't think I'm going to entirely accomplish in this question, but I'm going to postpone them at least. Okay, let's use that pivot of 1 to eliminate those entries under it. All right, we'll put this in reduced row echelon form. So we'll take row 2 and subtract 3 times row 1. We'll take row 3 and subtract twice row 1, producing something row equivalent. First row won't change. Let's see, we're subtracting 3 times the first row. 3 minus 3 times 1 is 0. 1 minus 3 times 0 is 1. Negative 1 minus 3 times 1 is negative 4. One minus 3 times 2, 1 minus 6 is negative 5. Now we'll subtract twice the first row. 2 minus 2 times 1 is 0. 1 minus 2 times 0 is 1. 1 minus 2 times 1, 1 minus 2 is negative 1. and 1 minus 2 times 2, 1 minus 4, negative 3. All right, let me check my solution here. We okay? We're okay. All right. Let's use that pivot in the second row. Let's use this pivot to eliminate the entries above and below it. Okay, fortunately, we already got a 0 above it. So we'll eliminate the entry below, and that ought to put us almost to reduce row echelon form. Third column might need a little bit of cleaning up, but we're close. So we'll take row 3 and subtract row 2. First row doesn't change. 1, 0, 1, 2. Second row doesn't change. Third row, here comes the arithmetic. Okay, let's see, 0 minus 0 is 0. 1 minus 1 is 0. Negative 1 minus negative 4. Negative 1 plus 4 is 3. And let's see, negative 3 minus negative 5. Negative 3 plus 5 is 2. I think all that checks. Okay. So to get the third column done, I see some fractions coming. Let's use that pivot, but maybe a cleaner version of it, to eliminate the two things above it. Okay, how about we divide that third row by 3. Here comes some fractions. Sorry, kids. We've avoided it as long as we could in this particular problem. So anyhow, we'll take our 3 and divide by 3. Okay, let's see, you need a bit more space here to get rid of the question. All right, so fractions give us, let's see, first row doesn't change, second row doesn't change. 0, 1, negative 4, negative 5. Third row changes because we did something to it. We divided it by 3 to get a 1 here and a 2/3 here. Bummer. Oh well. So now we'll subtract, as observed earlier. We'll use this pivot, very Gauss-Jordan-esque, to eliminate those two entries. Okay, that'll be cleanly done in the third column. Messy stuff in the fourth column because of the 2/3, but looks like it's unavoidable in this one. So we'll take row 1 and subtract row 3, and we'll take row 2 and we'll add 4 times row 3 to get the 0 entries. All right, I'll leave enough room to deal with those fractions. Let me show some confidence here. Yeah, if I've done the arithmetic correctly, we'll get zeros above that pivot. So we really only need to do arithmetic in a couple of entries. And then we've got a 2/3 there. Let's see what we get. Okay, so let's see, row 1, we're subtracting row 3, so we'll take 2 and subtract 2/3. 2 was what? 6/3 minus 2/3, should be 4/3. Maybe we can isolate that thirds. From row 2, we're adding 4 times row 3. So let's see, we're adding 8/3 to negative 5. Negative 5 is what? Negative 15/3 plus 8/3 is negative 7/3. Let me double check. Yeah. So, vector R with components, R1, R2, R3. Might want to write it as a row vector. it came out of a system of equations and should be written as a column vector. So that's a matter of taste more than anything. And we get, you know what, let me bring that 1/3 out front. We get 1/3 times the vector 4, -7, 2. Are we done? Question was, find the projection, hence, find the projection onto W of vector B. All right. And the way we found that was, we took the first R value, the second R value, and so forth, depending on how many vectors were in the generating set here of space W. Okay, there's only 2, so we'll just take the first 2. So what we get here is R1 times the first vector, 3, 1, 2, plus R2 times the second vector, 1, 0, -1. That's how you find projections onto subspaces. Don't include the third one. The third one, the -1, 1, -1, 1, 1 vector, that's all about W perp. And this is a question about W itself. And we had to find that stuff for W perp to know what to do. But it's a question about W, so we'll give an answer concerning W. Okay, let's see. R1, what do we have for R1? 4/3. So we get 4/3, 3, 1, 2. R2 is -7/3. Okay, so I'll simplify it a little bit. 4/3 times 3, it's 4. 4/3, 8/3, plus -7/3, 0, +7/3. So we get some common denominators at least. Let's see, 4, except for this one. 4 is what, 12/3 minus 7/3 would leave us with 5/3. 4/3 minus 0, this is 4/3. 8/3 plus 7/3 is 15/3. That's 5. And so we get 4/3. We have a little malfunction here. So I'm off in a third coordinate. 8/3, that's correct. 1, 0. Whoops. Whoopsie. Excuse me, kids. That third component was positive. Should have a +1 there. Let me fix my error in red and should have a negative there. Okay. So when we distribute the -7/3, we pick up a negative there. I subtract here, and we should have 8/3 minus 7/3. Well, I'm glad that happened. No, I'm not. But let me correct errors I make in a colored pen so you can see where they came from. I am kind of glad the numbers are a bit cleaner there. I can factor the 1/3 out and get something fairly clean, and that is the correct answer. So we get 1/3, 5, 4, 1, if you want to write it like that. Okay, so protocol was, as it's elaborated on in notes 6.1.A and 6.1.B. Now the manipulations was nothing new. It was a system of equations, and you solved that, and you found a null space along the way. Well, that's just solving a system of equations as well. And produced bases for W and W perp. If you were given a basis for W, you produced a basis for W perp. Then you wrote a given vector as a linear combination of those 3 vectors, which is, it's been a while since we've done this, but it's equivalent to this kind of manipulation. Put those vectors into a matrix as columns, augment with vector B, do your row reduction stuff. That gives you the R1s, R2s, R3s, and use the appropriate ones. You want to project onto W, just use the first 2, because the first 2, So that's why we take R1 and R2. The first two vectors were associated with W. Hey, what if you wanted to project onto W perp? I bring it up because we got all the equipment in front of us to deal with it. We'd take R3 times that third vector. Take R3 times that third vector, and that would give you the projection of vector B onto W perp. So kind of free information there since we've calculated all this other stuff. And that's how you project onto subspaces, which we'll use at length in the next section when we do the Graham-Schmidt process. See you then.